Okay, hello everyone. Welcome back from the break. Now we are roughly in the last 1/3 of the course, now I wanted to move on from the topics we've been discussing previously about the holography of information and discuss a little bit the story of islands and the page curve in ADS-CFT. Today, we're not going to reach the topic of islands, but we're going to embark on one of our detours. And I wanted to spend today's lecture just describing, how phenomenon entropy or entanglement entropy is computed in general in ADS-CFT. This is, background material that we'll use as we go on to discuss islands. So let me just start by describing the problem that we're going to consider. In fact, from now on and in the later part of the course as well, we're going to be discussing many things within the context of ADS-CFT, although we'll come back maybe later to flat space black holes. Let me just start by describing the problem that we want to understand today. And this is very closely related to the method of computing the page curve using islands. So the problem is as follows. We've discussed in many ways that, if you have some theory of gravity that lives in ADS, all the information about the bulk state is available in some small time band on the boundary. And of course, there's a more general proposal which says that in fact there's a conformal field theory that lives on the boundary that describes everything that's happening in the bulk. And the problem we want to consider today is as follows. Okay, so go. One second. That's interesting. Okay, great. Okay, so the problem we want to consider today is as follows. We have ADS. And so we have ADS. And on ADS, we take its boundary. So we take its boundary. And let's consider some region on the boundary. So not all the boundary, but just some region on the boundary. So say this region, which I've marked in thick lines, and let's call this the region R. Okay. So this is some region of the boundary. The question we want to ask is, what is the entanglement entropy of this region R with its complement? Okay. So notice that this, in this setup, I have drawn this region R as living on the boundary of ADS. But in fact, the question that we have asked is an entirely non-gravitational question that makes sense just independently in the conformal field theory. So I could just forget about the fact that this conformal field theory lives on the boundary of ADS. I could just independently think of flat space or Minkowski space on which the conformal field theory lives, or maybe I've identified it lives on S3 cross R. But I could just independently think of some region in which the conformal field theory lives, and then this is my region R. And then away here, I have R complement. So this is R tilde. Okay. And the question we want to ask is, what is the phenomenon entropy of the region R when this conformal field theory is put in some state? So I want to emphasize that this question is really a non-gravitational question. Previously, we have discussed many times, the issue of where we are considering quantum field theories. And we've said, we will write down some quantum field theory results, which will be valid in the limit that, the Planck scale is much larger than the scales of interest. But this question that we're asking right now is just a question in the conformal field theory, and there is no gravity. So there's no gravity. And the question we want to ask is, what is the entanglement entropy of R and R tilde in the CFT? And this is an entirely non-gravitational question. And in fact, in many cases, even the answer can be computed without making any reference to the gravitational bulk. Okay. Let me just say a few things about this entanglement entropy. Let me just make a few general remarks about this before we go on to talk about how it can be computed in theories with a holographic dual. Okay. So first, even though I drew the picture by saying that there was this region R and there was this region which was R tilde, in fact, the entanglement entropy is, depends, I've drawn these regions on a Cauchy slice, but in fact, the entanglement entropy, in fact, only depends on the causal diamond that sits on top of R. Okay. So I could have said, I can't draw diamonds very well, but let me try once again to draw a straighter diamond. But this is a causal diamond that sits on top of R. And I could have, instead decided to ask about the entanglement entropy of some other slicing. So I could have said, let me ask about the entanglement entropy of some other slicing where I've taken, maybe this R prime and have R tilde prime. So I chose to slice up the theory in some other way. But in fact, this entanglement entropy between R prime and R tilde prime is exactly the same as the entanglement entropy between R and R tilde. And that's because the entanglement entropy is really a function of the causal diamond. So it's something that depends on an entire causal diamond. So let me just explain why this is the case. And in fact, a little bit later in the lecture, the issue that we have here will be important. I see there's a question in the chat. The deformed slice still has to be Cauchy. Yes, indeed. So it still has to be Cauchy. In fact, the question we're asking here is, we have a causal diamond, and there's also a causal diamond that sits on the complement. Okay. So the question we're asking really is, what is the entanglement entropy between the causal diamond of R and the causal diamond of its complement? Okay, so it's all I want to say right now is that entanglement entropy is a function of causal diamonds. Okay, why is this the case? Let me just explain why this is the case. You see, the point is that the operator algebra of the causal diamond is isomorphic to the operator algebra of the base of the diamond. So in particular, let's say you have some point here, okay, and let's call this point Tx. Okay. And let's say there were some operators in this conformal field theory. There were some local operators. And I could have said, look here, I have an operator O of Tx. And that is different from the operators at time t equal to 0, because the operators at time t equal to 0 are O of 0x. And this operator is a different operator. But remember that in the conformal field theory, we have some relation that tells us that this is actually the same as O of 0x into e to the minus iht. And this is just coming from the fact that these are Heisenberg operators at a time t. Okay, but remember also that in the conformal field theory, the Hamiltonian is just an integral of some Hamiltonian density, which is a component of the stress tensor. So in fact, you can write h as integral of h of x dx, where this dx integral runs over the entire Cauchy slice. Okay, so the Hamiltonian is always given by integrating some local density in the conformal field theory. This would not be the case, for instance, if you were in theory of gravity, there, as we've discussed many times, the Hamiltonian is some boundary term. But here, we are just in a local quantum field theory. It's in fact a conformal field theory, and it's clearly Hamiltonian is some integral of some Hamiltonian density. And so if you insert this formula that we have here into this formula, so then you will see that the parts of this integral that are outside this region, that are outside the causal diamond, entirely, never enter into evolving this operator from here to here. Okay? If I wanted to evolve an operator here, I would never need to make reference to the parts of the Hamiltonian that live inside R tilde. So in fact, I could also write this as integral I h of x dx, where this integral only runs over R. Right? Where this integral only runs over R. So you see that even though initially I had a formula for O of t of x that said, I take O of 0x, I evolve it with the Hamiltonian, I can in fact rewrite that formula for any point anywhere in the causal diamond by taking some point at O of 0x, integrating the Hamiltonian only over this base R, and then evolving with that reduced Hamiltonian. And the reason for that is that the other parts of the Hamiltonian, there are other terms here, both those other terms commute with O of 0x by microcausality. Okay? So the reason this works is that the rest of the terms, so let me just write here, rest of the terms in H commute with O of 0x and in fact with O of t of x, with O of 0x by microcausality. Okay. And therefore, I can evolve operators from this point to this point using only this reduced Hamiltonian. But if you now stare at this formula that you have here, you see that this formula is a product of 3 operators, all of which are in the operator algebra of this base R. And therefore, it tells you that this operator O of Tx, in fact, can also be reduced to the operator algebra of the base R. Okay. So it tells you that, and because the operator O of T of x can be reduced to the operator algebra of this base R, therefore, all the information that lives inside the causal diamond can also be obtained from the region R. And vice versa. If you're given access to operators in the causal diamond, of course, you can get access to operators in its base. But if you're just given access to operators in the base, you can evolve and obtain the entire causal diamond. Okay. So entanglement entropy is not a function of the slicing of the Cauchy slice. It's a function of causal diamonds. And that's something that we will use. And it's an elementary fact, but it's useful to remember. Okay. Are there any questions about this part that we just said? Okay, great. So there's some very simple stuff. I just wanted to make sure we're on the same page. Oh, there's a question? Yeah.
Can I ask it's probably a stupid question, but if you consider a point on the region R, which is close to the boundary of the region,
yes,
then isn't that point connected causally to some points that are outside the causal diamond?
Yeah, so you mean this point here? But if I'm given initial data here, there is no way I can influence this point here from something here, because there's a light ray. I mean, I haven't drawn it very well, but this is a 45-degree ray. If I try to send a signal from here, I can't send a signal from here. Oh, of course, what happens here can influence what happens at later times, but I can't actually send a signal from outside this region to this point R prime.
Okay.
And if I try to send a signal from here, I fail because I can't travel faster in light. Of course, in the future, things go outside the causal diamond. So, but whatever I do, I have to send a signal which has to go through this region R.
But on the other hand, the region R can influence points that are outside the causal diamond.
Oh, yeah. The region R can in principle influence points which are outside. So there could be something which happens here. There are things which happen here for which you require information about both R and R tilde. So if you want to know what's happening here, like at this point, let's call it Y. Then you need information both about R and about R tilde. You can't get it, both R and R tilde. So the operators here, come from here, and they also come from here. So you need information from both sides. But within the diamond, you have information only about R that's enough to tell you what's happening within the diamond.
Thank you.
Okay, great. Okay, excellent. Okay, so that's very good. Now, of course, we can compute entanglement entropy in various ways. And in fact, in the next lecture, we'll discuss some ways that sometimes allow you to compute entanglement entropy in quantum field theories. But the reason this is of interest for theories of gravity is that in theories with a holographic dual, so in CFTs with a holographic dual, there is a proposal initially put forward by Ryu and Takenagi, and then by Humani, Rangamani, Takenagi, and then evolved by many people. And I'll write down the final form. So in CFTs with a holographic dual, there is a proposal for how to compute the entanglement entropy of the region R. And the proposal is that there is a geometric way you can use the bulk gravitational theory as a tool or as an auxiliary device to compute this thing. Okay? So the idea is to use the bulk as an auxiliary device to compute S of R. And the formula for S of R is that in the bulk, let me just write down the formula. Okay, I'll explain the terms in the formula. So the idea is that first you find an extremal surface which has area A and which is anchored on the region R. Okay, so A is the area of a bulk surface anchored on R. Okay, X here is the region between the surface and R. So let me just draw a picture and it'll become clearer. So for instance, if you have the picture that we had earlier, I'm just going to draw a cross section in time where R was some region here. So maybe this is R. Then the surface, you could find some surface, which might be, let me draw it in a different color, some surface of this kind. And this is now the area that we are computing is the area of this orange line. And X is the region in the middle, which is between the orange line and between the region R. Okay? So the claim is that you need to look at all such surfaces, and once you look at all, okay, sorry, I didn't explain what S bulk is. Okay? S bulk here, let me, one second, let me copy this to the next. Okay, should copy the formula as well. Okay, great. So S bulk here is the free field, or is some free field entropy of fields in X. Okay. So in principle, you could try and work this formula out to higher and higher orders in G Newton, but this is the formula that's correct to order G Newton to the power 0. And at this level, this is the free field entropy of fields in X. Okay. Now, what does this formula tell us to do? You see in this formula, you have a min and you have an X, and the formula instructs us to extreme, you're not allowed to consider any surface, but rather you take this term with in the inside brackets, and then you extremize the term. Okay. Now, why do we say extremize the term as opposed to just putting a minimum inside? So extremize often corresponds to, okay, so we are instructed to extremize the inner bracket. But you see, the reason I didn't write a minimum here is that if you think about this theory that we are considering, this theory in the bulk is a Lorentzian theory. And therefore, this area in principle could be reduced arbitrarily low, could be made as small as one likes, simply by moving the surface up or down in time. In the figure that you have on the slide right now, I've drawn everything on one time slice. But you see, I could move the area up or down in time. If you think of time as coming out of the slide, then I could move the area so that the surface almost becomes a light-like surface. And by doing that, I could make A by 4G as close to 0 as I like, just by making the area up out of various light-like segments. But when we are asked to extremize the inner bracket, that often ends up corresponding to maximizing in time and minimizing in space. Okay. The rule is you extremize, you look for an extremal surface, but you might what this often ends up corresponding to is that you maximize in time and you minimize in space. So you want an area that travels as little in space, but that you don't want it to travel about in time. That's not a valid way to reduce the value of A. Nevertheless, once you obtain a value for this extremum, you're then instructed to take the minimum of all possible extremal surfaces. And I'll explain the significance of this already in this lecture. Okay? So we take the minimum of all possible extremal surfaces. Okay. So I hope the prescription for computing this is clear. We'll do in this lecture an example for how this is done. But I hope the prescription is clear. I want to make a few more comments about this formula, or I should say one more thing. You see, sometimes there might be some subtlety about what kind of extremal surfaces we are allowed to choose. And when you do that, there's something called the homology constraint. And the homology constraint, one way to understand it, is that this region X has no boundaries except for the surface and R. So you're not allowed to, if there's some other boundary in the space, this region X shouldn't have some other boundaries. You're not allowed to make X, go and touch some other part of the boundary and come back. That's not allowed. So X should have no boundaries except for these extremal surface and R, and that's the homology constraint. Okay, I'm going to make a few more comments about this formula, but are there any questions about what the prescription is? I assume that many of you have seen this before, and this might be just a review for many, but if there are any questions about what the prescription is, we can take them now.
Yeah, could you explain what S bulk is?
Yeah, so S bulk is the free field entropy of fields in X. What that means is that let's say you have some quantum fields which are propagating in X. This formula makes sense when the bulk is weakly coupled. So when the bulk is weakly coupled, you might have maybe some scalars or some other fields which are propagating, and they might themselves have some entropy which you can compute for this region X, so that's S bulk X computed in this.
Yeah, so this X is a choice of the particular slice, right?
This X is this region which is shaded. This is X. I have written X here if you see, maybe it's not so clear. X
Right.
is like the region between the slice and between R.
Okay, and the variation is over X over here.
The what?
We're finding an extremum, so the variation is over what? So we are varying
the variation is over all possible surfaces. So you look for all possible surfaces. Every surface defines a region X, and then you look for the surface which gives you this minimum of this combination, the area by 4G plus S bulk of X.
Okay. Okay. Mm-hmm.
Okay.
I'm not sure about the maximum in time and minimum in space. Can you clarify that a bit?
Sorry, I was just saying, why didn't I write minimum? Why did I write min of X? Okay, I was just trying to explain that. This is within quotes. Okay, the rule is not that you should do this. The rule is just look for an extremal surface. You see, the reason we didn't write minimum is that if you had said, I just want to minimize area over 4G, then you could have moved the surface in time so that it could have become light-like. Right? Let me draw a picture to explain how that works. You see, let's say I'm trying to compute some region here, right? Now I could have said I can't draw. Okay, so say there's this region R which I'm trying to compute. Now I could have said, let's say this is time, my drawing. So I could have said, let me move down in time and let me move up here. Okay. Now this surface has an area that's almost zero because most of the time it's just moving in time. So I can move this, if I could try to compute the area of the surface, I could get 0. And therefore I can make the area as close to 0 as I like by moving in time. Is this clear? So, this region is a spatial region and I have time that's going on the y-axis. And I've kind of gone down in time and then gone up in time. So if I just put in minimum area, that would not make sense, because I could always make the area as small as I like by making the parts of the minimal surface almost light-like, and therefore we are instructed to extremize. When you're instructed to extremize, you try and choose the surface which maximizes in time. So you try and move as little as possible in time so that you get the maximum possible value, and then you minimize in space. Sometimes you might be forced to move in time. It might be that this surface that you have chosen. We'll consider examples in the next lecture when you're forced to move in time, and then you try and move as little as possible in time, so that you don't end up getting a large negative contribution from the dt squared part. Is that clear? Does that answer the question?
Yes, thank you.
Okay, great. Fine.
Suvrat, sorry, please go on. Please go on.
Yeah, go on. Yeah.
Oh, thank you.
Yeah, I also had a question. Oh.
Yeah.
I also had a question about the area term, because isn't it manifestly divergent if you couple it to the boundary?
I'm going to say something about that in a minute. Yeah, we'll discuss that. Yeah.
And excuse me, I have a question about your fifth comment.
Yes.
In that case, I remember some cases where, for example, paper by Hartman and Maldacena, where they consider end of the word brain, and they consider Ryuta surfaces ending on the end of the word brain. In that case, isn't the constraint violated?
No, so we will discuss ourselves such surfaces which end in the brain. When you put a brain in the region which has dynamical gravity, that's not counted as a boundary. So, and we'll ourselves do this maybe in the next lecture or the lecture afterwards. So when we say boundaries here, so when you put something, you're allowed to have surfaces which end on different parts of the brain. But here, boundary stands for it shouldn't. What we basically want to say is it shouldn't go and touch some other part of the boundary and come back from here. But indeed, we will allow. So brains are not counted as boundaries. So when you have brains, you have to be careful about how you phrase the homology constraint.
Okay, so
indeed you're allowed surfaces which end in brains.
So only asymptotic boundaries.
Asymptotic boundaries is one. That's one way. This is also important when, for instance, you start considering horizons. So you might have a situation where which surface you choose depends on the homology constraint becomes important. So one example where this becomes important, and maybe we'll discuss it a little bit later, is a situation where you have a horizon, and depending on whether you have an eternal black hole or depending on whether the black hole had formed from collapse, the homology constraint tells you that either the entropy is 0 or it's not 0. But indeed, brains are a special case where, you're right, they look like boundaries, but you have to be careful with the homology constraint in the presence of brains, and they're not really counted as boundaries.
Okay, thank you.
Yeah. By the way, I have to say the homology constraint is not, it's something that works, and it's something that's important to make sure that the prescription is consistent. But it would be nice to have a better understanding of the homology constraint. It's something that's imposed and that it's clear is necessary. But it would be nice if there was a completely rigorous derivation of the homology constraint, but actually there isn't. So, as in these cases where we have the brains, we do allow surfaces to end on brains and so on, and it would be nice to have have a completely clear statement that allows for that case and not for others. Okay. Are there questions?
Just one thing. Is this formula any different from the original RT formula, or it's?
I have added an XS bulk term, and I've put the whole thing inside the extremum. So if I had only the original RT formula, I would just have had an A by 4G term. I would not have. So there was an RT formula, and then there's an HRT formula that allowed us to do things where things were varied in time, and then you're careful, you had to have an extremum. And then there was a further improvement which said there's a one loop term you should add, and then there was a further improvement that said, well, you should extremize the sum and not just the area, and then add the one loop term. So all of these things will become important in some way or the other as we go forward.
Okay, thank you.
Okay, great. Okay, great. So let me say something about the UV divergence. So by the way, it's clear that both sides are UV divergent. It's not just that the right side is UV divergent, not just that the area is UV divergent. Everything here is a UV divergent. This is also UV divergent. So we need to match UV divergences. And as we will see, the fact that there are UV divergences doesn't mean you cannot extract cutoff independent quantities. And one reason, one thing that's clearly cutoff independent is the following. Okay, it's the subregion duality proposal. And subregion duality tells us that the CFT region R has information or is dual to the bulk region X. Okay. So you can think of this as a refinement in some approximation of ADS CFT. So let me just draw the picture so that it's clear what we're talking about. So R is some region on the boundary, and ADS CFT tells us that if you take the entire boundary, then the entire boundary is dual to the entire bulk. But the subregion duality proposal tells us something a little bit more fine-grained. It tells us that, well, if you had access to only part of the region on the boundary, if you had access only to the region R, then you would have information about the bulk region X. And we will have a little bit more to say about this as we go forward. And it's not entirely clear in what approximation this is true. It's probably true in some approximation where you think of simple excitations inside X. But this is one more thing that should be spelled out more clearly. But it's clearly also true that this formula is true in some sense. And so this is the proposal. Okay, so the proposal is that the CFT region R has information about the bulk region X. And if you think about point 7, you see it doesn't actually care about the UV divergences. Point 7 is not a statement about computing the entropy of the region R. It is a statement that you find a minimal surface. Once you find this extremal surface or minimize over extremal surfaces, the region X is unambiguously fixed. And it's true that the area A will diverge and SFR will diverge and so on. But the region that we are talking about is unambiguous. And the proposal is, that there is a sharp refinement you can make of the fact that the entire boundary is dual to the entire bulk. And the refinement is what I've written on the board. Okay, great. So those are two additional points I wanted to make. What I wanted to do now was spend a little bit of time just trying to make this more concrete by doing one very simple example of a computation, which I felt would be useful and would help to introduce what these formulas are. So the simple example of the computation I want to do is an example of a computation just in ADS3, where I want to show how we can compute the entropy of a region on the boundary of ADS3. So it's a particularly simple computation. And let me just explain what we want to do. Okay. So here is our boundary. This is the Cauchy slice. And on this boundary, I have some region. I can think of the boundary. I can rescale the boundary so that the boundary goes from 0 to 2 pi. Okay. And on this boundary, I have some interval that goes from 0 to some other region. Let's call it delta theta. And we now want to understand what is the entropy of the shaded region, the shaded yellow region with the rest of the boundary. Okay. So this is in fact a question that can be answered entirely just using CFT techniques. So this is the boundary is 1 + 1 dimensional in the example that we're discussing. And the question that I'm asking right now, what is the entropy of this region 0 to delta theta with the rest of the boundary, is one of the is a question which is particularly simple to answer just using CFT techniques, or at least can be answered particularly nicely using CFT techniques. And we will see, in fact, that there's an exact answer we can get. But this is also a question which serves as a simple test case for the formula that we have written down. Okay. So for the purposes of what we're doing right now, let me just consider the A/4G term and not consider the S bulk term. And let me just consider the A/4G term and ask what this A/4G term does. Okay, so what do we need to find? So what we need to find is some surface which goes from one part of the boundary to the other part of the boundary, the surface that I drew in white. And we need to find the extremal surface so that we extremize the surface And as we extremize this first surface, we will be forced to confront this issue of the fact that, we need to extremize the surface and their UV divergences and so on. And I think that this very simple example is useful to just understand how some of these things work. Okay. So what are we looking for? So remember that the metric of ADS3 is something that we have seen many times before. Okay, written in some coordinates, and theta here goes from 0 to 2 pi, and this is the metric of global ADS3. Okay, now in this situation, you see that if you want to extremize this area, then it's simplest, or in fact, just by symmetry considerations, we expect that this extremal surface will not move in time at all. Okay? So the extremal surface we expect will not move in time at all. And you see now why what I said about the fact that you didn't just want to minimize the area, but rather you wanted to extremize the area is important, because as we said, if you wanted to minimize the area, you would like to make it move in time. That would reduce the area. But if you want to extremize the area, then it's the simplest way by symmetry considerations is just not to make it move in time at all. And so we are looking for an R theta curve. So we are looking for a curve in R and theta. Okay. Now, in this situation, the extremal surface is just this geodesic that I've drawn. In more general cases and in higher dimensions, the extremal surface would really be a surface. But this is a particularly simple example because you can just parameterize the geodesic with some parameter tau that runs from 0 to 1. And then what we're looking to minimize or extremize is the following action. By 1 plus r squared into d theta by d tau squared d tau. Okay. Now notice that this is in fact a geodesic, but you should be careful that when you work in higher dimensions, sometimes when you work in higher dimensions, people use symmetry considerations and are often only trying to solve an ordinary differential equation. But you should be careful that in higher dimensions, you might often end up with additional factors of the metric because you really are minimizing an area and not a geodesic length. Okay? It just so happens that in 3 dimensions, we are minimizing a geodesic length, but in higher dimensions, that's not always the case. And you would usually end up with additional factors of the metric if you perform computations. And so it's useful not to get confused about that. But for this purpose, for what we're doing right now, which is a very simple case, we are really just trying to minimize this length. And then, of course, you can see that if you just wanted to find the minimal surface, you could just reparameterize the surface just as a function of theta of r, rather in terms of this tau. And therefore, you could just as well consider the action, which looked like 1 by 1 plus r squared into d theta by dr, the whole squared, and then integrate over dr. Okay, good. So now this is an action that all of us know how to minimize. I mean, it's something that we are taught, and you see immediately that there's a first integral of motion that you can get, and the first integral you can get is by noticing that there's a symmetry of this action under theta goes to theta plus constant. And the fact that there's a symmetry of this action allows you to immediately integrate and write down that from this action, the minimal surface, so theta dot is d theta by dr, which I'll write as theta dot, which is just c by r squared minus c squared and 1 plus r squared. This c is not the same as this c. Where I've introduced a constant. This constant comes from, so these two constants are different, by the way, of course. This constant just comes from doing the first integral of motion, and there's some constant just by doing one. This is just an integration constant, this c, and you see that this is what d theta by dr has to be. You can work this out. It's a very simple computation if you do this. Okay. So now you see, in fact, that there's a plus or minus here. You see that you have a choice of what the sign of d theta by dr has to be. And what does the fact that you have a choice tell you? You see, the fact that you have a choice is rather simple to understand. It's the fact that when you think of the surface is moving first in decreasing R. So first R decreases and then R increases. So if the surface is moving in a single orientation, if it's moving along some orientation of d theta, you see that the way you should think of the surface is that d theta by dr is first negative, and therefore R decreases. R decreases to some value which is R equal to C, and then it increases back to R equal to infinity. Okay, so I hope what is happening, what we expect d theta by dr to do is clear. You see, d theta by dr is going to first, we could take it to be first positive or first negative. I think the convention is, I chose a convention where d theta by dr is first negative because say theta is increasing and R is decreasing. And then d theta by dr is first negative, and then R decreases. When R reaches the value C, d theta by dr blows up because R is not moving at all, but theta is continuing to move. And then after that, d theta by dr switches sign and R goes back to infinity. Okay, so that's what we expect, and that's why we have a plus or minus. Okay, are there any questions about this algebra I'm doing? This is just some very simple algebra. So if there are any questions, I'm happy to take it. You can just do it on your own, but I'm skipping some steps in the algebra, but if there are questions, I can take them. Just feel free to interrupt. Okay, so I can integrate, of course, this d theta by dr. And if I do the integral, I will find that theta is theta naught plus cot inverse into c of square root 1 plus r squared by r squared minus c squared. This is along what we can call the ingoing branch, which is valid as r decreases from r equal to infinity to r equal to c. And then theta is theta naught minus cot inverse c into square root of 1 plus r squared by r squared minus c squared, and this is true along the return branch. So I've written theta as some piecewise function. In fact, theta is continuous. It's not really a piecewise function, but I've just written it because we chose these different signs for d theta by dr, and all of this together gives you the curve that we are looking at. And theta naught is this value, is the midpoint. Okay, so this is theta naught, and this is the curve that we are looking at. Okay. Now, of course, once you have this value of theta, you can also just plug this back into the original action and find the area. Now, when you find the area, as we discussed, the area will be divergent. When I write down the formula, you will see why. So I'm not doing anything here. I'm just taking the formula I had for d theta by dr and putting it back into the action. And when you put this into the action, you see that the denominator at large R goes like 1 over r squared. And that's because there are two terms that go like r squared inside the square root. When you take the square root, you get a 1 over r squared. But the numerator goes like an r. And therefore, the whole expression at large R goes like 1 over r. And 1 over r, if you were to do an integral all the way up to infinity, would diverge. And therefore, I have not done the integral up to infinity, but I have put a cutoff. I've put a cutoff at 1 over 2 epsilon. The factor of 2 is chosen just for convenience, but I've put a cutoff at 1 over 2 epsilon. And this cutoff is, it's not half epsilon, but it's 1 over 2 epsilon. And this 2 is chosen just for convenience. But you see that this is important because otherwise I would get infinity. As it stands, it's clear that I'll get some term which will go like log epsilon, which I will have to match with the UV divergence that I expect from the boundary. Okay. So if I do this integral, I will find that the area is minus log of 1 plus c squared plus twice log of 1 by epsilon. And the reason I put a 2 in the previous formula is because I wanted to get a 1 here. And now remember that we have this constant c here, but you can eliminate the constant c in favor of how much the surface has moved in theta. If you look here, you see that this constant c is related to how much the surface moves from here to here, right? And that is because if you just look at the formula, you will find that c is cot of delta theta by 2, where this that I have here is the difference in theta values of the endpoints. This formula, let me just emphasize, comes from this formula. Okay. It comes, if I look here, you see there's some surface which is centered at theta naught, and I can ask how much does the surface move in theta? And that is just, just happens to be cot inverse of C, or at least twice of delta theta happens to be cot inverse of C. And therefore C is cot of delta theta by 2. And I can substitute the fact that C is cot of delta theta by 2 back into the area. And I will find that the area is twice log of sine of delta theta by 2. Oops. Sorry. And divided it with some 1 over epsilon term, which I had previously. Okay. So that is my expression now for the minimal area computed in global ADS as a function of the size of the interval, which is delta theta. Remember, I've rescaled the boundary so that the entire boundary has size 2 pi. And this is some answer that I get. It is an answer which has this UV divergence, 1 over epsilon sitting there. But as you can see, there are clearly some parts of the answer that are cut off independent. And this is the answer that you get from a very simple computation. Some of you might have been able to see this immediately just by looking at the action, but it's a very straightforward computation. And so I just wanted to do it to show that there's no subtlety in doing it. Okay. Okay. So of course you can compute the entropy. The prediction for the entropy is just that A over 4G is 1 over 2G into log of the same thing, sine of delta theta by 2 into 1 over epsilon. Okay, now I said at the beginning that you could compare this with some answer that you could derive from the CFT. And how do you compare this with the answer that you derive from the CFT? You see, the first thing you need to do is convert the expressions that appear in this formula to CFT expressions. Now, one expression that appears in this formula is just sine of delta theta by 2. And of course, delta theta is obviously the interval of the CFT that you're comparing. There's no conversion that you need to do there. There is this 1 over epsilon. And as you can guess, that is going to go into a definition of a UV cutoff in the CFT. And then there is a 1 over 2G. That 1 over 2G, it is well known, and one of the first things we learn about ADS CFT is that the central charge, so let's call this Cn just to differentiate it from the C that we had earlier, which is the central charge of the CFT, is 3 over 2G. Usually you might see 3 LADS over 2G, but in everything we've been doing from the beginning, we've set LADS to be 1. And therefore, in these units, the central charge is just 3 over 2G. And therefore, the prediction for the entropy is actually the central charge divided by 3 into log of 1 by epsilon sine of delta theta by 2. Okay. Now you can independently show, just entirely independently, and in fact, before this formula was shown, it was shown in the 1 plus 1 dimensional CFT, that this formula is exactly the formula that you expect to get from in a conformal field theory. Okay? So this matches exactly with the CFT expectation. Okay. So this, in fact, was one of the things that was worked out the first time this formula was proposed. And it's a nice check of the fact that you write down this formula, which looks like A over 4G, which a priori looks like it has nothing to do with some entanglement entropy that was computed in a conformal field theory using entirely different techniques. But in fact, you can show that this matches exactly with the CFT expectation, where of course this 1 over epsilon needs to be matched with an appropriate CFT cutoff, but you can do that matching. The central charge dependence is unambiguous, and the sine of delta theta by 2 dependence is unambiguous. Okay, and this is one of the few examples where you can compute an entanglement entropy of the interval, which doesn't actually depend on any details of the CFT except for its central charge. It's like the Cardy formula for the entropy of 1 plus 1 dimensional CFTs, but it's a nice formula which doesn't depend on any details of the CFT. So it had to match with the bulk holographic computation. You didn't have any wiggle room there. And indeed, it does match with the bulk holographic computation. Okay, okay, great. Are there any questions about this part? Just to emphasize once again, there is a UV divergence, but let me just emphasize that, if you were to, for instance, compute d of s of delta theta by d of delta theta, that is something that is meaningful. The log of 1 over epsilon will just drop out. Let me also say that, so this is independent of epsilon. In higher dimensions, the story is a little more complicated. It's hard to get explicit formulas of this kind. And in general, the structure of UV divergences in higher dimensions might be more complicated. But that's something that can also be worked out in some systematic way. But for our purposes, and just to have an example, this example is the simplest, where the structure of UV divergence is also very simple. Okay, great. Are there any questions about this very simple computation to demonstrate how this formula works?
So there is no S bulk here.
Thank you. That's a good question. So there is an S bulk here, but the point is that if you're in the vacuum state, which is where this formula works, that S bulk will also end up giving you some term which is proportional to the area. Okay. And that will end up here in a renormalization of the Newton's constant. Okay. So for this very simple case, that S bulk term for the vacuum, it will just end up renormalizing the Newton's constant. So you will have to define a renormalized Newton's constant, which takes into contribution that expression from S bulk as well. S bulk would become more interesting if you started considering other states, which were not the vacuum of the CFT, but which had some excitations. And then you would need the S bulk to match the bulk in the boundary answers. And that has also been done in some examples. But for the vacuum case, S bulk doesn't really have any contribution. I mean, there's some UV divergence, but that you can just absorb into a renormalization of the Newton's constant.
So, quick question. Yeah. So, on the CFT side, can you remind me is this entropy calculation? So you said it's universal, but what sort of universal properties of the CFT does it depend on? Is it just the Virasoro symmetry, or also modular invariance?
So the way this computation is done is that you take, so you want to compute the entropy of a diamond, and you can take a diamond and you can map it conformally to the half plane. So even though you have a diamond here, you can actually map the diamond conformally to the half plane. So you can make a conformal transformation so that you're thinking of Rindler instead of a diamond. In the Rindler case, you actually know what the modular Hamiltonian is, and therefore you also know what the modular Hamiltonian is in the case of the diamond. You then just need to work out some expression in terms of that modular Hamiltonian, and that's particularly easy to do in 1+1 dimensions because that modular Hamiltonian is some integral of the stress tensor, and the stress tensor OP is closed. So if you're trying to work out some expression of the stress tensor, that's something that you can just work out exactly because the stress tensor OP is just closed and only depends on the central charge, and it doesn't depend on anything else. So the way this computation is done is by doing this conformal transformation to the half plane and then back.
Right. So I'm trying to understand if there's something, if I should consider this as a non-trivial check of RT formula, or is it something that had to be true? Because just given the symmetries on both sides, there's really only one answer you can write down, because the 2-point function is fixed entirely by symmetries. The fact that you have conformal transformation that maps, that's also something that's a property just of the symmetries of CFTs.
Okay. Let's see. Did it have to match? I mean, maybe, once you know the answer, maybe you could have argued that it had to match, but there's some structure to the answer here. There's some sine of delta theta by 2 that's coming about. So there's some non-trivial structure to the answer. Maybe you, but I would have expected
the sine of delta theta is fixed by symmetries. Perhaps the only non-trivial thing I can see in this formula, if any, is the coefficient, is the fact that the coefficient matches exactly.
Yeah, sure.
The coefficient I think should be fixed by symmetries.
Yeah, you're right. The coefficient, the coefficient A over 4G had to match. I mean, if you'd written down A over 2G, you would certainly have been in trouble. So the coefficient indeed had to match, but there's one coefficient which you could fix here. Yeah, I'm not sure. Maybe you could have got a lot of things, and maybe these things had to work. I mean, in the original paper, Ryun Takinagi kind of said, it's almost clear that this has to work for similar reasons. So if you read the paper, they have comments of this kind saying, it's almost clear this has to work. I mean, that's how they hope that something like this might have worked. Yeah, I'm not sure if maybe one can just dot all the I's also and cross all the T's. You're right. I mean, it's not. Yeah, okay. Maybe it's not. If you think about it carefully enough, it may not be an extremely strong check. But I mean, it's nice that this very simple test works out.
Yes, of course. Okay, thank you.
Okay, great. Yeah. Okay. So now let me say a few words about the question. Yeah.
There's a question in the chat asking, does the expression for central charge come from holography?
The expression for central charge, yeah, that comes from the that's the standard ADS CFT. I mean, the expression for the central charge is the first thing we know about ADS 3 CFT2. If you want to match the Virasoro algebra, you have to make sure that the central charge works out correctly. So, okay, great. Okay, so let me say a few things about the entanglement wedge, which I think will already lead us into some things which are interesting. So you see, there's now a proposal. So there's of course a proposal for the fact that we have some answer for the entropy, but now we also have a statement about the entanglement wedge. Right? And the entanglement wedge statement is telling us that look, I have some region R on the boundary, and I have the shaded region, and in fact this region R knows about, so this goes from say minus delta theta by 2 to delta theta by 2, and this region R on the boundary knows about the shaded region in the bulk, right? Now, how can we understand this in some other way? And in fact, I want to explain that in this case, for this very simple case for the interval, this is something that we can check. Okay, so this subregion duality proposal just for this interval is something that makes sense. Let me first point out that on the boundary, as I said at the beginning of this lecture, we have this interval that goes from minus delta theta by 2 to delta theta by 2. But in fact, you could also think of the causal diamond. So you could think of the causal diamond that went up to delta theta by 2 and went up to minus delta theta by 2. So remember, time goes on this axis and theta goes on this axis. On the boundary, you just have t and theta. So in fact, although I drew this region R, the claim is really that the causal diamond on the boundary has information about the shaded region in the bulk. Okay. Now, is there some way we can actually check that? So in fact, one way to check that is to note that every point in the shaded region, okay, if you take any point in the shaded region, let me just draw some random point here, okay, then there is a time-like trajectory that connects this point in the bulk to some point on the causal diamond here. Okay, so I can't draw the causal diamond, but there is a time-like trajectory that connects every point in the bulk inside this wedge to some point on the causal diamond. And let me just give you a quick check of how you can see that. Okay, so consider this point, okay, which is sitting at say theta equal to 0, and which is sitting at R equal to what we were calling C, okay, which is sitting at the low. That's in some sense the point that is most distant from the boundary. And what I want to show you is that a light ray starting from this point at R equal to C will reach the boundary exactly at the tip of this causal diamond, at the past and future tips of this causal diamond. And from there, you can persuade yourself that if you take some other point inside this wedge, there is a time-like trajectory that would connect it to this causal diamond on the boundary. Okay, so let me just show you this very simple computation. So let's consider some point which is sitting at R is equal to cot of delta theta by 2, okay, and it's sitting at theta equal to 0 and t equal to 0. Okay, and the question is, how fast can it reach the boundary? Okay, so remember that a light ray has to move along dt is equal to dr by 1 plus r squared. This could be plus or minus. It could either move forward in time or it could move back in time. And therefore, a light ray to reach from R naught to infinity takes a time which is just given by cot inverse of R naught. Okay? That just comes from integrating the expression that we have here. And therefore, if you think of a light ray that starts from this point, let's call this point P. So a light ray from point P reaches the boundary precisely at the tip of the causal diamond. Exactly at theta equal to 0 and at t is equal to delta theta by 2. Okay? And that just comes from the fact that you have to take cot inverse of R. R itself happens to be cot of delta theta by 2. You take cot inverse of that, you get delta theta by 2. And therefore, if you start at t equal to 0, you reach the boundary exactly at t equals delta theta by 2, which proves the claim that I made previously, which is if you start here, you will reach the boundary on the tip of this diamond. Okay? And you can convince yourself that, in fact, this is true for every other point. You don't have to move at the speed of light. You can move in a time-like trajectory. You start at some point here, you will end up, there's a time-like trajectory that will connect you to the boundary. So that's telling you that the geometry of what you're seeing here is the following. Okay? The geometry is that you have some region on the boundary, and this thing that we are calling the causal wedge. So this is the causal diamond on the boundary. And now this one. And this thing that we are calling the causal wedge is causally connected to all parts of the causal diamond. So this is what we're calling X. So this X is this region which, if you draw a cross section in time now, if you draw a cross section in theta now, looks like this. Okay, so this is how if you draw this in the TR plane and you draw also the causal diamond, then this is how the geometry looks. Okay, so it is not surprising.
Yeah. I have a question about So I mean, what if the innermost point lies inside the horizon? I mean,
the innermost point will not lie inside the horizon. There are no horizons here. The RT surfaces generally do not penetrate horizons. But here we're just talking about empty areas. It's a very simple example.
Okay.
So there's no horizon here. I mean, we can just the subregion duality proposal is believed to hold in all cases, including cases where there's a horizon and so on, but there's no horizon here. This is just
so this is statement you are right now making is for the free. I mean, not the vacuum case.
I'm just giving an example of how. So what I'm trying to do right now is, I said in the beginning that there was a subregion duality proposal, and I'm just giving an example of how in this simple case we can understand it in a different way. And then, although I'm going a little slower than I want, I will then give you an example of another case where the entanglement wedge or this region X is more non-trivial, and where we can't understand it using these simple techniques. So I'm just giving you a simple example of a check of this subregion duality proposal. I'm not saying something very general about entanglement wedges.
Okay, yeah. So thanks.
Okay, great. So let's say so the point is, when you have a geometry of this kind, so let's say let's take a simple example. Say we have a bulk field phi. Okay. Say we have bulk minimally coupled field phi. And in fact, these are the kinds of examples for which the subregion duality proposal makes sense, where you take some minimally coupled fields, which are almost free, and then you consider low point correlators in those fields. And let's say this field obeys some equation, which is of this kind. Then the point is that if you're given a geometry of this kind, you might be able to solve this equation radially inwards, subject to the boundary condition that the limit as r tends to infinity of r to the delta phi of r t theta is equal to O of t theta. Okay. So if you're given this boundary condition on the diamond, so in this situation, if you're given this boundary condition here, you might be able to solve this equation radially inwards just by solving the partial differential equation. Usually you tend to solve hyperbolic partial differential equations forward in time, but you could also solve this partial differential equation inwards in this way. And you could expect to get, therefore, a solution for phi of r t theta in this wedge here, or in this region here, in terms of O on the boundary. Okay? And in fact, this is something that one can do explicitly, and one can write down at least, so I'll explain what the subtlety is, but one can indeed write down a formula that says R of t prime, theta prime is given in terms of O of theta t, and some kernel which can be written down explicitly, t prime r, and where this integral over d theta and dt goes over the boundary diamond. So this is an explicit map for a simple case, and this k can be written down explicitly. I have to say there's a slight subtlety which I'm kind of brushing under the carpet. In fact, this map is written down explicitly in momentum space, not in position space, for a subtlety that I don't want to discuss, but I'm happy to explain more. Is not important for our current discussion. But barring the subtlety, you can write down explicitly an expression for bulk fields in this wedge, or on this region X, and also in this entire wedge in the bulk, in terms of boundary fields O. Okay, so remember, let me just remind you that this is the geometry that I have here. And let me just remind you of this formula. Okay, so this formula, in fact, can be written down entirely independently of any Ryuta-Kanagi calculation. It's just a formula that you can write down by solving the partial differential equation subject to some boundary conditions, and that allows you, that works as long as r theta phi is in the entanglement wedge. And by entanglement wedge, I mean what I have drawn below, which is the region X and the causal completion of X towards the boundary. Okay, so this is a formula that one can just write down, and this gives you a check of subregion duality in this very simple case. Okay. Is this clear? So this is one check of subregion duality. I'm now going to give you an example of a case where the subregion duality becomes more interesting. Okay, great. So in this case, we have a situation where we can explicitly understand subregion duality. And now, why am I harping on this issue? The reason I'm harping on this issue is that this subregion duality is very important, and in fact, it will be very important when we turn to understanding islands. And it is not difficult to find examples of non-trivial entanglement wedges. So I want to now give you an example of a non-trivial entanglement wedge. Okay. So the idea is that rather than considering one interval, let's start considering two intervals, right? Nothing told us that the region that we had to take on the boundary had to be a single connected region. I could have just as well taken a union of two regions. So I could, for instance, take a setup where I have this boundary, and then on this boundary, I have this region, and I have this other interval here. And let me, just to make life simple for myself, take this one going from minus delta. Oops. Let me take this going from minus delta theta by 2 to delta theta by 2. And this also going, having at least this, so actually, I don't want to write down coordinates. I just want to say that the length of the size of the intervals on the boundary is the same. And I have these two intervals that are the same length, but they're on opposite sides of the boundary. And then I can ask, what is the entanglement entropy of the union of these two intervals with its complement? So R is a union of two intervals. Okay, so now, of course, if you wanted to do this, now this is already a situation where in the CFT, the answer becomes non-universal. It depends on which CFT you're computing. But in the bulk, we have a formula for the RT surface, and the formula for the RT surface tells us, you should just work out the minimal extremal surfaces. And of course, we know what the extremal surfaces are. Well, what are the extremal surfaces? Here are some extremal surfaces. Let me draw them. Here is an extremal surface. And these are clearly extremal surfaces that we are allowed to choose and which will give us the entropy of the union of these two intervals. Okay? But now notice that we also have some other extremal surfaces, right? Because we also have some other intervals which are complementary, and these intervals have a size which is given as pi minus delta theta. So we have some intervals here which are complementary. The complement of this region is also given by union of two intervals, and these intervals have size pi minus delta theta. And we can also ask what is the entanglement entropy of those intervals of the complementary regions. And you see that the complementary entropy is also computed by RT surfaces, and those RT surfaces are the white surfaces, and they do something of this kind. Okay? But notice now that the white surfaces are also good. They also satisfy the homology constraint for the union of the yellow intervals. Okay? So you see that for both cases, both for R and for R complement, if I wanted to compute the entropy, I have now a choice of two RT surfaces in the bulk. So we can take the union of orange surfaces or the union of white surfaces. So both of these surfaces are good for computing the entanglement entropy of the union of these two regions. And the question is, which is the entropy that we should choose? Which is the surface that we should choose? In fact, in the beginning, we spent some time discussing this, and we said that the correct answer is that you should choose the minimum area surfaces. You should first extremize the area, and then if you have more than one possibility, as we do here, you should choose the possibility which leads to a lower entropy. So let's copy this and let's go here. Okay. So now it's clear that for delta theta being smaller than pi by 2, the entropy is given just by the orange surfaces. And that's because if you take delta theta to be very small, you can picturize in your mind, the orange surfaces will become smaller and smaller. So there's some UV divergence, but the UV divergence is the same both in the orange and the white surfaces. The question of the difference between the orange and the white surfaces is independent of the UV divergences. If you take delta theta to be very small, then it's clear that the orange surfaces have smaller area than the white surfaces. And therefore, for small delta theta, it's clear that you have to choose the entropy given by the orange surfaces. On the other hand, as delta theta becomes larger, and the point at which it switches is when delta theta becomes larger than its complement, which happens when delta theta becomes larger than pi by 2, you see that the entropy is given by the white surfaces. Right? And that's because when delta theta is large, when delta theta becomes larger than pi by 2, then the entropy of the white surfaces is smaller than that of the orange surfaces. Okay. So let's copy this once more because I want to emphasize what's happening. Okay. So for larger than pi by 2, it's the white surfaces that win. So let me in fact erase the orange surfaces. So now the statement is that, in fact, when you consider the union of these two intervals, you should compute the entropy of the union of these two intervals, not by taking the surfaces that go from one interval to itself, that connect one interval to itself and the other interval to itself, but rather you should take these surfaces which connect one interval to the other interval. Okay, and these are the surfaces which have minimum area. But now the entanglement wedge proposal tells us something pretty interesting. It tells us that so this is the new surface. It tells us that the entanglement wedge is this region that I'm shading here. So even though individually, these regions could only describe like something much smaller. When I take the union of these two regions, and provided these two regions are large enough, they can describe this region, this larger region, which extends all the way, which is the blue shaded region that I drew. Okay. In fact, it is guaranteed that this is something that it is guaranteed that this is something that will it is guaranteed that this is something that always has to happen either for R or for the complement of R. You see, if you go back to the previous diagram that we have here, we said that for delta theta smaller than pi by 2, the entanglement wedge was the old entanglement wedge. It was a union of the old entanglement wedges. So the orange surfaces win. But when the orange surfaces are winning for delta theta, if you were instead to focus on the complementary regions, then you see that the orange surfaces are winning for the complementary regions as well. And therefore, the correct way to compute the entropy of the complementary regions would also be by taking these orange surfaces. Okay. And so the claim is, you see, and that's not surprising because S of R is equal to S of R tilde. So either for R or for R tilde, the entanglement wedge is non-trivial. Okay, so EW is entanglement wedge, and the entanglement wedge is non-trivial. Okay. Now, why is the fact that the entanglement wedge non-trivial interesting? Okay. It's very interesting because you see that previously, just a few minutes ago, I said, well, you know, in the case when the entanglement wedge was a simple entanglement wedge, we had an independent way of understanding why the entanglement wedge, you know, why subregion duality worked. And that independent way of understanding relied on the fact that every point in the entanglement wedge was causally connected to this causal diamond that lives on the boundary. But now notice what happens. Let me put back in the old surfaces that I had. Let me shade them in. Okay. So now there is some region which is between the orange surfaces and the white surfaces. Okay, so there's some region. Let me shade with. Okay. That's this region in purple, which I've now shaded. And this region in purple is, or whatever the color is clearly out of causal contact with the diamonds that are built on top of delta theta on the two sides. Okay, so points here are out of causal contact with the boundary causal diamonds. Is this clear? So you see, we are saying that these boundary causal diamonds have information about these points. And earlier, what we said was not so surprising because the points we were saying the boundary causal diamonds had information about were points that were in causal contact with the boundary causal diamonds. But now we are saying that if we believe the subregion duality proposal, the boundary causal diamonds have information about some points that are out of causal contact with those causal diamonds. Now, this is important, in fact, because when we discuss islands, this is precisely what will happen in the case of islands. So this is not an island. This is not what's conventionally called an island. But in some sense, it's a manifestation of the same phenomena, which is the fact that the entanglement wedge, if you take the subregion duality proposal seriously, can often be non-trivial. And this is the simplest example where the entanglement wedge is non-trivial. Now, why is this interesting in other ways? You see, just to emphasize why this is interesting, notice that if I were to try and write down, I cannot have in this case, if I were to write down phi of r t theta O of t theta, if I were to write down a formula of this kind, dt d theta, and integrate this over r, and try and say this formula is valid in the entanglement wedge, such a formula would clearly be wrong. Okay? This formula cannot work. It cannot be the case that the bulk field is given by taking some simple boundary operator and just by smearing it with some simple kernel and thereby obtaining this bulk field all the way inside this non-trivial entanglement wedge. This formula that we wrote down that did work inside this region, in the between the orange curve and the yellow curve, does not work for this larger entanglement wedge. And the reason it cannot work for the larger entanglement wedge is very simple. You see, it is the fact that if I take some point inside this larger entanglement wedge, so let me take some point here. Let me call this point P. Okay. Then you see that phi bulk at the point P and O anywhere for any point in R. You see, in the bulk, gravity is dynamical, and therefore we don't have micro-causality. It's something that we have emphasized many times in this course. But in the presence of gravity, it may happen that you get non-trivial commutators, even at space-like separation. But the point is that if you compute a commutator of two simple operators, both of these are simple operators, you expect that this is something that is suppressed. It's suppressed by 1 over n, or it's suppressed by G Newton. Okay, and this is clearly inconsistent with having a formula of this kind. Okay? If I were to say that I have a formula of this kind, let me just copy the formula. Okay. Then it cannot be the case that the commutator of phi and O is of order 1 by n, because if you had a formula of the kind that I have written here, the commutator of phi and O at some point would have to be order 1. It cannot be that the commutator of phi bulk and O is always order 1 over n. The commutator would have to be order 1, which is indeed the case. If phi itself can be written in some form of O, then of course, you can write phi dot in some other simple form in O. And therefore, you would have expected that there's some combination of O you can find so that the commutator between phi and O is order 1. But just causality or approximate causality in the bulk tells you that if you have this non-trivial entanglement wedge and you take the field phi or some quasi-local field phi and insert it in the middle and try and compute the commutator of the boundary, that commutator has to be suppressed because these points are space-like separated, whatever point you take in this boundary causal diamond. And that itself tells you that the answer for how the bulk is represented in terms of the boundary cannot be just by doing some simple smearing in this way and by smearing some simple boundary operator with some kernel. So it must be the case that even for this case, the information in the entanglement wedge lives inside some complicated operators in R. And this is yet another example of how when we start taking complicated operators in theories of gravity, and the bulk here is gravitational, the notions of locality that we have might break down. This example that we have clearly tells us that if you are to believe this subregion duality proposal, then there must be some sense in which complicated operators in R can look much further than simple operators inside R. Okay. Are there any questions about this part?
I have a question about earlier.
Yeah.
S of R equals S of R tilde, you said. So that is the case trivially if only the area term is there.
No, S of R is equal to S of R tilde because the boundary state is in the vacuum. So when the boundary state is pure, as we said, the eigenvalues of the density matrix of R are the same as the eigenvalues of the density matrix of R tilde. And then, we expect that the entanglement entropies are the same.
Okay. So
from
the RT formula also?
Yeah.
Is the same with the RT formula also, right?
The RT formula will indeed give you something that's consistent with this. The RT formula had to, and that's because you're picking the minimum. you see, it's a reason. It tells you that this minimum part of the RT formula is important. If I had just said, pick some extremal surface and put some constraint, then, and if I pick the orange line, the orange curve for delta theta, and I pick the white curve for pi minus delta theta, I would get different entropies, and that would be inconsistent. And therefore, the minimum part of the RT formula is consistent with the fact that the entropy of a region is the same as the entropy of its complement when the whole system is in a pure state. Putting a minimum ensures that you're always picking the same RT curve, both for the region and for its complement.
Okay.
Yeah. In fact, yeah, go on. Yeah.
Yeah, I got maybe a more conceptual question.
Yes.
Because it feels like like we have some sort of phase transition when causal arguments are enough to encode the information, and then we suddenly will need more complicated. Yeah. So I know there is some interpretation from this from bit threads, but is there maybe another way we can?
Frankly speaking, I don't have a good understanding of this, why this happens. At least I don't. I don't think we do. I don't think in that there's a good understanding in literature. But maybe some people feel they understand this clearly. But at least I don't have any clear understanding of how this works. I think it's a very interesting phenomena how this happens. In fact, I see that we're out of time. So maybe tomorrow's lecture I can start by explaining. How we also previously in this course many times discussed how information is localized unusually in gravity because the Hamiltonian is a boundary term, but that by itself is not enough to tell you what's happening here. And I'll explain that in the beginning of tomorrow's lecture because we're out of time. But I don't actually have a good understanding of what leads to this phase transition. In fact, I think we can say a little bit more. Not only do we not have a good understanding of what leads to this phase transition, I said here that, you cannot, for this larger wedge, write down a formula of the kind that we have written down in cross below this formula, that we just to say is wrong for this case. In fact, it's not even clear that there is a good formula that you can write down independently. If you were to assume the subregion duality proposal and you believe that, it is the case that this entanglement wedge is described by these delta theta regions, then under that assumption, you can write down some formulas for what the field phi has to be in terms of the boundary operators. But I don't know of any a priori way, or you could have written down that formula without having made this proposal in the first case. So I think this is an example of a situation that I think, at least I think, should be understood much better. And I think it's very interesting, and it's already an example of how entanglement wedges can be non-trivial. Which is already visible even in empty ADS. We don't need to go to islands to do that. It's already an example. So this is a long-winded answer of saying that I don't have a good understanding to your question, which is that I don't really have a good simple way of explaining why this happens. But it is a prediction of the subregion duality proposal. And I think it's a very interesting prediction that we should have a better understanding of in terms of direct bulk reconstruction, which I think we don't. Yeah, in fact, I think we're out of time, so we can just take a few more questions, I think, and then we can continue tomorrow.
Can I ask two quick
Yeah, go on, yeah.
So, the first one is related to this one, and it's
yes.
If you have an operator in the bulk which is still, let's say, in the previous entanglement wedge, but after the phase transition, is that encoded also in a complicated way in the bulk diamond or not? In the boundary
probably
diamond?
not. No, if you took some point like here, then I think you would still be able to write down a formula of this kind. So if you put this in the old causal wedge, or people make a distinction between what's called the causal wedge, which was the simple entanglement wedge we had now, and the entanglement wedge, which might be this more complicated case. Then you could delete the crosses. Then it would be a correct formula. I mean, there's nothing that says that the old thing that you had stops working, but the old thing that you had works only up to the orange line. It doesn't work beyond the orange line. I mean, the old formula is very simple because it's just based on solving some partial differential equations in the bulk. So as long as the bulk is weakly coupled, the old thing will not fail. But you can't make the old thing work beyond the orange line. Even after the phase transition, it will work, but only up to the orange line.
Thank you. And the other question is, what's the reason to actually claim that proposal? Like, if you have the causal wedge, then it makes sense that the bulk duality, bulk subregion duality. But if you have this complicated causal wedge, is that is there any evidence to claim that or not?
Yeah. So the strongest argument comes from the fact that if you use, if you try and compute the bulk relative entropy, that is the same as the boundary relative entropy. So the argument here is that the bulk relative entropy is the same as boundary relative entropy. So the relative entropy is, you can think of as a measure of distinguishability. If two states are distinguishable, then they have some non-zero relative entropy between them. So relative entropy is an entropy. I mean, you can think of it as an entropy, but really it's a notion of distance between states. If you believe this proposal, for which there's evidence, the fact that the bulk relative entropy is the boundary relative entropy, then this tells you that two states which are distinguishable in the bulk in this entanglement wedge are distinguishable in the boundary regions R. Okay. So if you remember this formula that I've written here, and you go back here, the formula tells you that if two states are distinguishable in this bulk, in this larger bulk wedge, then they are also distinguishable in the boundary, and vice versa. And that's why, the statement would be that if, it would be like the statement we made earlier, that if you can distinguish two states are distinct in the bulk, then there's some operator on the boundary in this delta theta region that can distinguish between them. So the strongest evidence for this proposal comes from this fact that the bulk relative entropy is the same as the boundary relative entropy. And that's where this proposal comes from.
Okay, thank you.
Yeah.
So for the case of delta theta greater than pi/2,
yes,
the region X is in the middle, right?
It's the whole region. Yeah, I mean, I shaded this region purple to indicate the non-trivial part, but the whole region, which is in blue, like the messy blue region, that's the region X.
And if you're calculating the entanglement entropy of the complement surfaces,
right,
then you have X on the left and right.
Exactly, X on the left and the right hand side. Exactly.
The S bulk in those regions must be the same as the S bulk in the middle.
The bulk part, in the vacuum case, the bulk part, as I said, will just turn into some area term. So it'll just renormalize the Newton's constant. Are you thinking of a non-trivial state maybe? Or, a non-trivial state?
Yeah.
Yeah, if you're a non-trivial state, then yes, it would be the case that, the S bulk in those parts is same as, but that's clear because, the state in the bulk is pure. So it should be the case. But go on, please, with your question.
No, that's it.
Yeah, so that would be true. Yeah, that you would have some, those things would be the same. Right. Are there any other questions about this?
Yeah, I also had a question related to the earlier ones.
Yeah.
The operator needs to get access to the information in the middle, so in the purple region. Those complicated operators, do they need to live on both of the yellow regions, or can they live on just one of the yellow regions? Because I would assume that usually they would need to make a reference to both regions, right?
Yeah, they would need to make a reference to both regions. It's clear they have to make a reference to both regions, because if you had only one region, then you could there is an entanglement wedge proposal for that as well, which says you can see up to the orange line and you can see no further. So whether you take simple or complicated operators on one region, like one delta theta, maybe the region on top, you can see only up to the orange line and not beyond that. And similarly for the region below. So if you take simple or complicated operators below, you can see up to the entanglement wedge, which is up to the orange line, and I can hide information if I go beyond that. So it's somehow the fact that if I combine now operators from the top and from the bottom, I can see further than I can do with either one of them. And I mean, yeah. So you need operators which live on both regions. It's clear they have to have complicated operators and they have to live in both regions. In fact, maybe that's already clear. That already tells you, maybe actually that's that already tells you that, some formula of the kind that we have below would be in trouble. Right. Does that answer the question? I hope it does.
Yeah, definitely. Thank you.
Yeah, okay, great. Are there any other questions?
Yeah. So what is the status of this entanglement wedge when delta theta is exactly equals to pi/2?
When it's exactly equals to pi/2. I don't know if that question is well understood. You mean when it's I don't know if you understand this proposal at that level of precision to ask what happens exactly at delta theta equals pi/2. I mean, it's clear what happens at delta theta equals pi by 2 minus epsilon and what happens at delta theta equals pi by 2 plus epsilon. But you know, that it might be even a question of the order of limits and how you take the limits, whether you take the limits from above or below and so on. So I'm not sure it's a very well-defined question. And it might depend on the question of how you take. You know, there's a discontinuity in the entanglement wedge, right? So when you have a discontinuous function of this kind, it depends on how you take the limits, whether you take it from above or from below.
But the entanglement entropy is continuous function of delta theta.
Correct. The entanglement entropy is continuous because at delta theta equals pi by 2, these regions, the orange and the white regions, have the same area. So at some point they switch, and that's indeed important, right? It shouldn't be that the entanglement entropy changes discontinuously. So the entanglement entropy changes continuously, but the entanglement wedge in the bulk changes in this funny way.
Oh, okay. Yeah, thanks.
Okay,
great. I also got a question, and I don't know if you can answer this, but for ADS, it's sort of clear that the holographic theory lives on the boundary, and it feels like this is quite an important fact to determine the causal wedge. But if we have other spacetimes like Minkowski or the sitter where we don't really know where the microscopic theory lives, can we make similar arguments? Then we don't really have a causal wedge, right? Or
yeah, I mean, so you know, we did discuss Minkowski, and we said that there we believe that the information should be available on the past boundary of future null infinity, but the geometry is a little bit different. You know, if you look at Minkowski space, so we were saying that, you know, the information should be available everywhere here, and maybe that might be a good place. I mean, we don't have a good understanding of the duality, but that's probably a good place where, you know, so remember, this is I plus minus. So we said, you know, so I've drawn a cone here. So I've drawn the future null infinity as a cone and past null infinity as a cone. These cones are distinct as we discussed, but you know, so you might say that the boundary theory or the dual theory should live here. But the point is that things work a little bit differently. You know, you don't the operators here and the operators here at like different paths, they just totally factorize. So you have, you know, they're just totally disconnected from each other. And so you don't have this notion of entanglement in space. I mean, you'd have to work harder to come up with the notion of entanglement of this kind. You know, if you draw some region on this boundary here, there's some clear sense in which there is spatial entanglement on the boundary of ADS. To ask about spatial entanglement on null infinity is more complicated because, you know, null infinity kind of breaks up at different values of theta into like independent theories that live at different points of null infinity. Okay, that doesn't say very precisely the answer to your question, but you know, if you wanted to define some analogous notion, I mean, people try and define these wedges and so on. One would first have to answer this. You know, one would first have to understand in what sense like different parts of null infinity are entangled with each other. Now, if you go around the celestial sphere, in what sense are different parts of the celestial sphere entangled with each other? That's not a very good answer to your questions, but you're right. We don't have a good understanding. I mean, there's no proposed generalization of this formula to other cases where you're not in ADS. I don't know if if Prahar is still on the call. I don't know if you want to say something about this, Prahar.
No, I don't really have really much to add on that.
Fine. Yeah. Yeah, I mean, I think the answer is that we don't have a good generalization of this away from ADS CFT. So it is kind of important to be on ADS on the boundary of ADS. In some cases, you know, maybe, yeah.
No, I'll just add one paper. I can't remember the authors. There was just, so in ADS, there's this work that where you can, if you assume the RT formula, then you can derive, in the bulk, you can derive Einstein's equations. So you assume that you have a CFT with some entanglement entropy, and you assume it has some holographic dual. Right. And you don't know what the bulk metric is, but you assume that the geometry of the bulk satisfies the RT formula. So any entanglement entropy you compute can be then obtained from some minimal version of the surface. And then there's this is work by Onkar Parikar and also and a bunch of his co-authors.
Yeah.
I know of a work which has done the same thing in in flat spacetime as well. They have conjectured some version of the RT formula where they look at some sort of geodesics emanating out from Scri+, and they were able to show that if you assume their conjectured version of the RT formula, you can reproduce the bulk linearized equations of motion in Minkowski spacetime. So yeah, I don't think that's been well established, but I do know that there's at least one conjecture out there.
Okay, thank you.
But I think this is how they like conjecturing the RT formula to work for more cosmological spacetimes. This is in general what is used in literature, right? For example, if you study islands in cosmology, or I feel like this is.
Yeah. I mean, I don't have something very precise to say about it. I mean, there's some sense in which we can make things work. But I mean, the island proposal in some sense will go a little bit beyond this. So maybe actually that's already one example. When we discuss the island proposal, which hopefully we'll come to tomorrow or maybe next week at the rate we're going, it'll be a case where we will be using holographic techniques to compute the entropy of some region that is not actually living on the boundary of ADS. So the whole point of the island formula is that we consider a more general situation where you take this boundary and you extend it, you couple it to some bath. And then in this bath, you have some region, and then you want to compute the entropy of the bath using only the fact that, the state in the bath came from the evaporation or some state in ADS. So that you might say is already some generalization of this formula. It's the fact that the region you're computing now doesn't live on the boundary of the gravitational region. And in fact, that's why it is an island formula. So that you might already consider to be an example. And so those kinds of examples one can construct where, you have some region, there's a non-gravitational bath, and then you want to compute some entropy of that. But I mean, there are other generalizations also that you'd like to make, like maybe to Minkowski space, but at least I don't know how that can be done. I mean, yeah. Apart from the case that Prahad just mentioned.
Right. Thank you very much.
Okay.
I also have a question.
Go ahead. Okay.
Okay. So I just wanted to ask, in this picture of entanglement wedge that you have, I think the purple region can be reconstructed using the PETS map, right? And that is state dependent, while for example, HKLL formula that you wrote for the region between the orange surfaces is not state dependent. I was wondering if you can say a few words about that and whether this state dependence is the same sort of state dependence that you actually proposed.
So I don't have, I mean, in this case, we don't need to be, so we don't need something to be too state dependent because we want to do a reconstruction about the vacuum. So in fact, in many of these cases where we even if you use complicated operators, you see, we want everything to work in the little Hilbert space about the vacuum. So we have the vacuum of ADS and we have some excitations on top of that. And then we want some formula that works within that subsector of the Hilbert space. So, you might write down something that looks like it's state dependent, but it's not really state dependent, because if you just have one little Hilbert space in which you want things to work, you don't have to use state dependence. Even if you write down something that involves the modular operator and the flow of the modular operator and so on, which is how, for example, this Faulkner-Liukowitz reconstruction, this wedge would go. It would not be something, it might look state dependent, but in fact, because you know already which little Hilbert space you're on, it's not really state dependent. So the state dependence issue comes about when you start discussing typical states in ADS CFT. And then you want something to work in one state here and some other Hilbert space, and you want it to work for all sorts of typical states, and then you need some state dependence. Whereas here, I think what you're referring to is the fact that if you were to write down some reconstruction, which I emphasize, assumes first that something like this works, and then you can write down various variety of formulas. Then such a thing might involve like operators like the modular operator, and it would look like it's state dependent. But that's not what one would really call state dependence, because you just want it to work in one little Hilbert space. So you know ahead of time what the little Hilbert space is. You can just plug in the modular operator ahead of time for that little Hilbert space. And so I think this would be a little different from the kind of state dependence that we will discuss in a few lectures from now when we discuss large black holes in ADS.
Thank you.
Okay.
Sorry,
yeah, go on. Yeah.
I think it's just one small technicality, but at some point we said that S of R was the same as S of R tilde.
Yes.
Isn't the correct statement that S of R at delta at some delta theta is the same as S of R tilde at pi minus delta theta, that delta theta?
Oh, S of R and S of R, what does delta T and pi minus delta T mean?
Delta theta is the size of the thing that we call delta theta, the size of the
this is what I was calling R, and this is what I was calling R tilde. R tilde is the complement of R.
Yeah.
So this is just the fact that, so R tilde and R are regions of different sizes, but it is just a general fact in a pure state that the entanglement entropy of some subsystem is the same as the entanglement entropy of its complement, because the density matrices have the same eigenvalues.
Yeah, okay.
So that's why S of R is always this, and you see that from the formula, because either the orange line spin or the white line spin, but it's the same for both of them. I think we had somewhere curve here. Yeah. So the S of R is really the same as S of R tilde. Whether it doesn't, even though R and R tilde have different sizes, it's still true that S of R is same as S of R tilde.
Yeah. Okay. Thanks. Makes sense.
Okay. Okay. Are there any other questions?
Yeah, I had another question, because I was thinking about this phase transition, because if this delta phi is larger than pi over 2, then it has to be, if you take the two disconnected regions, that the second part of the region purifies some part of the first region. So then it's clear that it needs to have more information than the sum, right? So.
Sorry, why is it clear that? I didn't understand. Why is it clear if I take this to be like let's take this diagram. Let's say that this is exactly delta theta is like pi over 2. So everything is pi over 2. So now, why is it clear that
pi over 2? Well, if it gets larger than pi over 2, then they will have to purify each other, considering the state is pure as a whole, right? Because then you would take more than half of the.
That's true. That's true. Yeah. You're right. They would have to purify each other. Yes, indeed. You're right. And so that would tell you that
they will have more information than the sum, right?
That is true. Yes, that is true, that they would have more information than the sum. Yes.
But does that explain why it has more information, so to say? Or?
It's consistent, but it's certainly, it's consistent, but I don't think it explains why the shape changes in this way. You're right that beyond some point, the union of the two sides is like larger than half. And so the part which is larger than half has information, but I'm not sure it explains why the entanglement wedge jumps in this way. There's something quantitatively precise that's happening in the bulk that we are saying, right? There's some precise set of points in the bulk which are dual to something that's happening in the boundary, and it's some precise and geometric thing that's happening in the bulk, which probably would not happen if you just had it wouldn't even make sense if you didn't have a holographic dual. So you're right that that it's clear that when the phase transition happened, it had to happen at delta theta equals twice delta theta equals pi, because that's the point at which the region becomes larger than half. And so it's consistent with that, but I don't see from here immediately why you would have to have this jump in the entanglement wedge. Maybe if you have something I'm not understanding or something more you'd like to say.
No, it was just a speculation, and I wanted to see what you thought.
No, I agree with you that your observation is right, that this is the point at which the union of the two regions is becoming larger than half, and so that's the region where you would have expected something to happen, and so that's correct. But I think there's something more that we should understand here.
Okay, yeah, that helps. Thanks.
Sorry, if no one has other questions, I'm still not. I can't completely see why S of R is equal to S of R tilde from the discussion that we were having before. Because visually, the length of the surface that we consider for R and R tilde are very different if R is large, for example. So R tilde is small.
Yeah, but you see, you have to pick the minimum. So either you pick the white ones or you pick the orange ones. So you see, you have the choice of white and orange for both R and for R tilde. So let's say if orange wins for R, then orange also wins for R tilde. If white wins for R, then white also wins for R tilde. You see, you can always pick the same RT surface for R and R tilde. I mean, the fact that S of R is S of R tilde is independently true in the CFT, but I guess your question is, why does the RT formula implement this property of the CFT?
Yeah.
Because I mean, this is just a general statement in a quantum field theory that in a pure state, the entropy of a region is the same as entropy of its complement. But the RT formula implements it because you can always pick the same. If the whole state is pure, you can always pick the same RT surface for a region and for its complement, as we see in this example as well.
So S of R tilde is computing S of R tilde doesn't mean using R tilde as our initial R, which would give.
It does mean that, but you see, this is R tilde. But even for R tilde, you have two RT surfaces, right? You have this surface and you have this surface. So let's say we forgot about R. Let's say R tilde was the one we're interested in. But even for R tilde, you have these surfaces you're interested in. Yeah. So either you could take like the ones with single crosses or ones with double crosses, no? So both for R and for R tilde, you have a choice of RT surfaces. And you make the same choice in both cases.
Oh, yeah. Yeah, okay, thanks. Perfect.
Okay.
It's clear now. Sorry about
that. Okay.
Thank you.